let's get right into it. Today, we're exploring the absolutely fascinating hidden world of semiconductor manufacturing. We're going to look closely at how factories actually measure microchips while they're being built. Now, you might think it's as simple as just looking through a really powerful microscope to see if the circuits work, right? But the reality of quality control at the nanometer scale is this incredible, mind-bending logistical puzzle.
And here's a crazy truth to kick things off. For the vast majority of its journey through a fab, a semiconductor isn't an electronic device at all. You can't turn it on, you can't measure its current. Instead, it's purely a product of physics and chemistry, just a wildly complex layering of microscopic materials. It actually doesn't become an electronic device until the very last layer is sealed.
To make sense of how we actually guarantee these chips work, here's our roadmap. We'll start with how the measurement journey begins, look at front-end physical checkpoints, uncover the test key secret, tackle the invisible enemy of defects, cross the electrical bridge with Watt, and finally, wrap up with back-end chip testing. Okay, part 1, the measurement journey begins. If you want to understand how we measure chips, you absolutely have to grasp this massive divide between the front end and the back end. The front-end factory, the IC fab, is entirely about building the physical structure. Think of it like constructing a giant skyscraper. You're out there checking the thickness of the steel, the width of the hallways, making sure the floors align. It's all physical, chemical, and optical. The back end, on the other hand, is about testing the electricity once that skyscraper is totally finished and plugged into the grid. To put that front-end construction phase into perspective for you, a typical advanced chip goes through over 1,000, sometimes up to 1,200 individual processes. I mean, imagine baking a cake with 1,200 steps. If you mess up step 47, the whole thing is ruined, but you wouldn't even know until step 1,200. And that is exactly why inline sampling, checking the work literally while it's happening, is crucial to catching errors early. Moving right along to section 2, front-end physical checkpoints. So where are the actual toll booths in this massive 1,200-step marathon? Well, whether engineers are blasting wafers with high-temperature diffusion at over 1,200 degrees Celsius or physically grinding them down with CMP, they're basically checking one main thing: physical thickness. They just need to make absolutely sure those physical layers are exactly as thick as the recipe calls for. But then we get to lithography, using light to print the actual circuit patterns, and things get incredibly sensitive. We aren't just measuring thickness anymore. We're using specialized scanning electron microscopes to measure critical dimension, or line width. But the real make-or-break metric here is overlay. Because we're building these chips layer by layer, if the overlay alignment is off by even a fraction on a 3-nanometer or 5-nanometer process, that entire integrated circuit is basically garbage. Which brings us to section 3, the test key secret. Okay, plot twist time. You'd probably assume that with all these ultra-precise optical tools, the engineers are constantly inspecting the customer's actual super valuable microchip as it goes down the line. But actually, no. That's a massive misconception. They don't want to risk damaging these incredibly complex proprietary chips. So instead, the factory relies on something called a test key. These are specialized monitor patterns safely hidden away in the streets, which are just the tiny grids of empty space between the actual product dies on the wafer.
So here is the big takeaway. Factories measure the streets, not the chips. By scanning the thickness, the line width, and the overlay of those test keys sitting in the streets, the fab can safely deduce that the valuable chips sitting right next to them are being built perfectly. It's an absolutely brilliant way to monitor quality without ever touching the actual merchandise.
Let's pivot to section 4, the invisible enemy, defects. Now we're fighting the environment itself, because line widths today are unfathomably narrow. A single microscopic speck of dust floating around can easily bridge 2 printed lines. At the 3 or 5 nanometer scale, that one little speck of dust is literally a lethal short circuit. And hunting these particles is a total nightmare, because dust is unpredictable. It's not tied to a specific chemical recipe. To find them, fabs are moving from optical scanners to highly precise e-beam scanning. But there's a huge catch. E-beam scanning is incredibly slow. Because they can't possibly scan every layer of every wafer, engineers have to use their hard-earned experience to guess exactly where in that 1,000-step journey they should hit pause and hunt for these invisible enemies. All right, section 5, Watt, the electrical bridge.
We finally made it. At the very end of the front-end line, the physical structure is complete, and it is time to cross the bridge into electronics. This is WAT, the wafer acceptance test. It's this magical moment where our giant physics and chemistry project finally receives electricity. We check the electrical health of the wafer right before it leaves the front end. But remember our secret from earlier? Even here at WAT, we are still only running electricity through the test keys in the streets. We still haven't touched the actual ICs.
And fabs have to perform a massive balancing act here. They usually sample 5, 9, or maybe 21 points across the wafer. If you measure 21 points, you get incredibly accurate data about how consistent the wafer is. But that severely slows down factory throughput. Plus, the electrical data files generated are so ridiculously huge that engineers usually have to take them completely offline just to crunch the numbers.
And finally, Section 6, Back-end chip testing.
If the wafer actually survives WAT, it physically leaves the front-end fab and enters the back-end packaging world. Now the whole process shifts. First, we do chip probing to map the wafer. Then, the wafer is literally sliced apart right down those streets we've been measuring all this time. Finally, those individual dies are packaged into those familiar black plastic squares we know from our consumer electronics, leading right into the final test. And this is a total paradigm shift. In the front end, we relied completely on random sampling of the streets, just to see if the factory machines were behaving. But the back end? Random sampling goes completely out the window. Because absolutely nobody wants to buy a broken chip, every single packaged chip gets a 100% full electrical inspection before it ever leaves the building. So look at what we've covered. We went from measuring nanometers of thickness to hunting microscopic dust to running full electrical diagnostics. But all this data we collected isn't just about passing one wafer today. It's the foundation for the future. With thousands of data points on millions of wafers, how will fabs use this massive ocean of data for AI-driven yield analysis to build the impossible chips of tomorrow? Well, that's an explainer for another day. Thanks so much for joining me, and keep questioning how the world around you is built. Catch you next time.